Well, hi science friends. I just spent the last hour recording this without sound, so hopefully we've got sound now. But I'm going to try to run through this really quick because that was not the way I wanted to do that. So, hope you all had a good Thanksgiving break and you all got a little extra rest. We are going to do a little bit of stoichiometry today. So last week we did some stoichiometry, but today we're going to incorporate some different conversion factors. The conversion factors we're going to use today are converting between molecules. So remember, in 1 mole, we've got 6.022 times 10 to the 23rd molecules. That's Avogadro's number. So we're going to use that today. You should be familiar with that conversion, but you've not used it in stoichiometry. And then we've also got our 22.4 liters per 1 mole that we're going to use today. So we're going to practice stoichiometry with a couple additional conversion factors, but same old stoichiometry that we did before Thanksgiving break, just adding a little bit to it. So I've got a couple examples for you, and then I will let you do a couple of practices with each one. So, how many molecules of oxygen are produced when a sample of 29.2 grams of water, so this is what they are telling us, so we know that we want to start with that, 29.2 grams of water, is decomposed by electrolysis according to the balanced equation. So because the coefficients are there and it tells us, we know that this is the balanced equation, so we don't have to do anything to it. But remember, you always want the equation to be balanced before you start. So it's asking us for molecules of oxygen. That's what we are trying to find, okay? So now electrolysis, let's just talk about this for 1 second. It says it's decomposed, so it's a decomposition reaction, and you should recognize that from those reaction types we've talked about. What electrolysis is, it has 2 words there, electro and lysis. Lysis is a word that we use in biology a lot, and it means to break down or to break apart. And so electro is implying electrical current. And so water is decomposed by electrical current to break it apart. And so that you can put water in electrical current and break it down into hydrogen and oxygen, and this is the equation that shows that. So 29.2 grams of water. So what we're always trying to do is get to moles. We need to get to moles if we want to go from water to oxygen. We have to go to moles first. There's no other way to get from water to oxygen but through the mole ratio. Okay, so let's get this grams of water. I know I have to have grams of water on the bottom because I need those to be able to cancel out. Okay, and we can go from gram to mole, okay, using our molar mass from the periodic table. So the molar mass, if we add it up for water, 1 oxygen and 2 hydrogens, is 18 grams of water per 1 mole of water. So now that I'm working in moles up here, I want to put my moles of water on the bottom, so again that I can cross it out, and I can use my mole ratio. So my mole ratio tells me that there's not 1 water, but there's rather actually 2 moles of water. And we're trying to get to oxygen, so we want to look at the mole ratio of oxygen. So there's no number there, there's no coefficient, so that just means it's 1. So 1 mole of oxygen, okay? And we know, like I just mentioned a moment ago, that 1 mole of oxygen, we're trying to get to molecules, and 1 mole of oxygen has 6.022 times 10 to the 23rd molecules of oxygen, okay? So I want to make sure that I set this up entirely correct, and so I'm going to cross these out, grams and grams of water, moles of water, moles of water, moles of oxygen, moles of oxygen, okay? Please, 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 please do that step, okay? If you can do that step, you've probably got it set up right, and you're probably going to get the answer right. If you can't do that step, I can guarantee it's wrong, okay? Almost. So, unless by some fluke thing. So then we're just going to multiply through and divide. So 29.2 times 1, which is nothing, times 6.022. Now I'm going to leave off times 10 to the 23rd for right now. We'll come back to that in a minute. So I got 175.84. I'm just going to leave that in my calculator. Divided by 18, and then divided by 2. So I got 4.88. And then we still have to tack this part back on there. 4.88 times 10 to the 23rd molecules of O2. And that should be your correct answer. Okay? Now, there's 2 more Eutrites. I want you to go ahead and do both of them. Pause the video here. Go ahead and do both of them. And then I'm going to show you the answers. Okay? Pause now. So coming back, we have these problems. So you should have gotten for this first one 4.8 times 10 to the 22nd molecules of O2. So these were set up pretty much just the same. If your answer differs very slightly, it's probably because you did the molar mass of potassium chlorate different. Maybe you did 122.4 or 123. That's okay, as long as you got something pretty close to this answer that I have. It doesn't have to be exactly spot on. I'm more interested that you can do the steps than you can get the answer down to the exact decimal place. Okay, but we started what they gave us, 6.54 grams of potassium chlorate. Then we did the molar mass ratio. Then we did the mole ratio. And then we went to molecules. And you should have got 4.8 times 10 to the 22nd molecules of O2. Okay, let's take a look at the next one. This one again was very similar, except we were going from molecules to grams. Okay, so we started with what they gave us, 5 times 10 to the 22nd molecules. Okay, and then we said we knew that 6.022 times 10 to the 23rd molecules made up 1 mole. Okay, then we set up our mole to mole ratio, 1 mole of nitrogen oxide per 3 moles of nitrogen dioxide, which is what we're trying to find. And then the last step, we did our molar mass. Okay, now in this one, what I did when I multiplied it in my calculator, I multiplied 5 times 1 times 3 times 46. And then I divided that by 6.022. And what I got was 144.6, okay? And then I remembered that I still have this scientific notation part. So what I have is 10 to the 22nd divided by 10 to the 23rd. And if you do that and you divide scientific notation, what you actually do is you just subtract the exponents. So 22 minus 23 gives me this 10 to the negative 1. So 144.6 times 10 to the negative 1. So truly, to express that in the easiest way, you would write it as 14.46 grams of nitrogen dioxide. Now, I wouldn't count against you if you wrote it as 144.6. Maybe you wrote it in scientific notation as 1.446 times 10 to the first. That's technically okay too. But that's just, I personally would have written it as 14.46. But any of those combinations would be fine, okay? Again, I want to see that you can do the work, not that you can express it in a specific way, okay? So let's do one more together here, okay? Assuming STP, so I think we've talked about, I don't know that we've talked about STP very much. STP stands for standard temperature and pressure. We'll use it a lot in the next unit when we do gas laws. But all standard temperature pressure means is that we're going to use that 22.4 liters per 1 mole, okay? At standard temperature and pressure, that's how much volume any gas takes up. If you're not at standard temperature and pressure, it's not 22.4 liters per mole anymore. It's a different amount. So at STP, that's what it is though. So that's just what it's telling you to use. So our question is, how many liters of oxygen? That's what we're trying to find here. How many liters of oxygen are needed to produce 19.8 liters of sulfur trioxide? So that's what I want to start out with, 19.8 liters of sulfur trioxide, because that's what they've given me, okay? So then I'm going to use this conversion factor. I know there's 22.4 liters of sulfur trioxide in 1 mole of sulfur trioxide. Okay? Then I'll use my mole ratio. I have in my equation, 2 moles of sulfur trioxide. And it's asking me about oxygen. So there's only 1 mole of oxygen in the equation. And then it wants to know liters of oxygen. So in 1 mole of oxygen, there are 22.4, 22.4 liters of oxygen. Okay? And so I want to make sure that I've done this correctly, so I'm going to mark out to check. Please, 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 please do this step. Okay? So it looks like I'm left up with liters of oxygen, which is what I want. So I'll put this in my calculator, 19.8. Now, I'm also going to mark out 22.4 because it appears top and bottom, and you can do that, okay? Because otherwise all you're doing is multiplying by 22.4 and dividing by 22.4. So then really all I have is 19.8 divided by 2. But if you forget to do that, it's no problem. It'll still work out the same. But you should get 9.9 liters of O2, okay? And that should be how you work that one. So again, you have 2 more practice problems to try. They both are very similar to this problem. So again, you'll use this 22.4 liters per 1 mole ratio, and then the mole ratios that are given in the balanced equation. Okay, so you work with these 2. Pause me now, and then we'll come back together and discuss them. So here we are back to look at these problems. Again, what we did first, we started with what we knew, which was that 3.86 liters of carbon monoxide. I went to 22.4 liters in 1 mole of carbon dioxide so that I could get to that mole to mole ratio. Okay, once after I got that mole to mole ratio, I went back, to again 22.4 liters of oxygen. Okay, and then I could cross through that 22.4 liters there and basically just divide 3.86 divided by 2, and you should get 1.93 liters of oxygen. Okay, let's go ahead and look at the next one. It was very similar. You had a 4 to 6 mole ratio there, and I got 0.28 liters of PH3. Okay, so hopefully you all got those. If you're still struggling with those, of course, reach out to me. I want to do one more here together, and then I will turn you loose to your assignment for today. So let's look at this one. Nitrogen monoxide and oxygen gas combine to form the brown gas nitrogen dioxide. How many milliliters of nitrogen dioxide, that's what I'm going to try to find, are produced when 3.4 milliliters of oxygen reacts with an excess of nitrogen monoxide? Okay, so I'm going to write down what they give me to start with. 3.4 milliliters of oxygen. Okay, so there's really a couple of ways that you could do this, but what you should recognize here is that it's talking about milliliters. Okay, our conversion factor is 22.4 liters. So we can't just roll with this 3.4 milliliters. That's not going to work very well. So we can either convert 3.4 milliliters to liters. We can convert our conversion factor, 22.4 liters, to milliliters. Or we can set up a really big stoichiometry problem. Okay? I'm going to convert 3.4 milliliters to liters is what I'm going to do. Okay, so 3.4 milliliters, if you remember, Kentucky has dark, deep coal mines. So here I am in the milliliters, and I'm wanting to get to liters. 1, 2, 3 places to the left. So if I take this 1, 2, 3 places to the left, what I have is 0.0034 liters. So I'm going to start with that instead, 0.0034 liters of oxygen. Okay? All right, and then I can just work the problem as normal. Okay, so I know that there are 22.4 liters of oxygen in 1 mole of oxygen, and my mole ratio here is 1 mole of oxygen per 2 moles of nitrogen dioxide, which is what I'm trying to go to. And then in 1 mole of nitrogen dioxide, there's 22.4 liters. Okay. Now, if I want to go ahead and convert this to milliliters, I can do this in my stoichiometry problem. In 1 liter of nitrogen dioxide, there's 1,000 milliliters of nitrogen dioxide. You can set up a conversion factor like that, okay? That's optional. If you want to leave this last piece off and just work it to here, that's fine too. And then you can just use Kentucky Has Dark Deep Coal Mines and convert. However you want to set it up is fine, okay? If you wanted to put that at the beginning, do 3.4 milliliters of O2 and had done 1,000 milliliters per 1 liter of O2 and then carried on with this next step, you could have done it that way too. You got a lot of options really as to what you do here, okay? And I don't care how you do it, so long as you know what to do, okay? So let's go ahead and work this how I have it written. 0.0034. I'm a little messy as to what I've got written at this point. I'm going to go ahead and cross out these 22.4s because they're the same. So 0.0034 times 2, okay? And then I'm going to go ahead and multiply by 1,000 also. And what I should get, there's nothing on the bottom for me to divide by, is 6.8 milliliters of NO2. Okay? Now, had you not have multiplied by 1,000 and you just did 0.0034 and then times 2, you would have got 0.0068 liters, right? And then you could have gone up here and said, I need to move that 3 decimals to the right, 1, 2, 3 decimals to the right, and then you would have gotten 6.8 milliliters, which is the same, okay? So any way that you do it, you'll get the right answer as long as you set it up correctly. So always be mindful of those, always kind of be looking out for those prefixes and making sure everything is in the right unit. You can't use milliliters with liters without converting something, okay? So you all go ahead and get started on that stoichiometry worksheet too. Let me know if you have any questions, and I will see you all later. Have a great day.